This is the second video over the AP Chapter 1 through 3 review. So I'm going to go through a few of these. Let's do number 13. 13 is more of a lab-based question, but it relates to mass percent. It says the mass percent of carbon in pure glucose is 40%. A chemist analyzes an impure sample of glucose and determines that the mass percent of carbon is 38.2%. Which of the following impurities could account for the low mass percent of carbon in the sample? So it's supposed to be 40, but it's actually lower, 38. So there's something lighter in there with it, making the overall percentage lower for carbon. Now if you take a look at some of these, like if you take a look at ribose, the percent of carbon in ribose is going to be about the same because it's a 1:1 ratio. So the empirical formula is actually the same, 1:1 ratio. So the amount of carbon on ribose is the same, which means you won't really see a difference. This will not contribute to the error that we see. Fructose, same idea. It's also a 6:12:6, so 1:1. Sucrose is actually a little less. It's 1, 2, and then less than 1. So this, this is not really correct, but 0.9 or so. So there's actually more carbon in sucrose. So the water is the winner, and that's because when there's a little bit of water in here, there's really no carbon in water at all, which means it can make it seem like there's less carbon if there's a bunch of water present. So the lower percent is due to the water. Let's take a look at number 15. So we got ourselves a hydrate. Apologize. A little more room. Take a look at 15. So we have a hydrate, and we have 3.22 gram sample of this hydrate. Now remember, a hydrate is where a water molecule is incorporated into the ionic formula. And we're going to try to find what this X is. How many water molecules are there? So we begin with 3.22 grams. Now that's of the hydrate with the water in there. And after the water is driven off, the mass of the anhydrous without the water is 1.42. So the value of X in the hydrate. This is going to be more like determining the empirical formula of a compound. What we need to know is how many moles of water we have for every mole of our original compound mass. So let's do this. The compound weighs 1.42 and the molar mass is 142. So little quick math, 1.42 over 142. This is like doing 1 divided by 100. This gives you 1/100th or 0.01 moles of our sodium sulfate. Now the water that's driven off is, we can calculate how much water has been driven off if we do 3.22 minus 1.42. It may be easier to do it this way, 42. You get yourself 0 here. 12 minus 4 is 8. So we got 1.8. Here's the 1. So we have 1.80 grams of water. Well, can we find out how many moles of water? We sure could. We know that molar mass is given to us as 18. Divided by 18. This is like 1 divided by 10. This gives us 0.1 moles of water. So here are our two pieces of information. We have 1/100th of a mole of sodium sulfate and 1/10th of a mole of water. You see that we have 4 times the number of water as we have sodium sulfate. So this, not 4 times, 10 times, I'm sorry. From here to here, we have 10 times the amount, which means there are 10 water molecules in each formula unit. And that's how you go about solving it. All right, number 16. Take a look at number 16. Here we have a compound that contains these molar amounts. So 1.10 mole K, 0.55 mole tellurium, 1.65 mole oxygen. What's the simplest molecular formula of this compound? Simpler formula of the compound. So we know that we have twice as much K as we have TE, right? So here, look, we got 1.10 K, only 0.55 TE. So K should be double TE. So let's pick the ones where K is double TE. So here is K is not double TE. That's the other way around. Here K is double TE. We're good here. Here K is double TE. This one's out. Quadruple. This one's out. So that dwindles us down to 2 possible options. Now let's take a look at the relationship of oxygen to tellurium. Here we have 0.55 mole of tellurium and 1.65 moles of oxygen. So does that look like 6 times more or 3 times more? It looks to me like 3 times more oxygen than we have tellurium. So this then would be the answer. Good. And then in order to determine the actual empirical formula, we could do a little number. There's a little trouble. So why don't we do number 19? So take a look at number 19. So here we'll be able to get the empirical formula and then the molecular formula. Remember, the molecular formula is higher than the empirical formula. Empirical formula is the most reduced formula. Molecular formula is a little bigger than that. So we have a 27-gram sample of an unknown hydrocarbon which was burned to form 88 grams of carbon dioxide and 27 grams of water. What's the possible formula? So if we have 88 grams of carbon dioxide, remember the way to do this is you would first go percent to mass, mass to mole. Let's outline those steps as we're going to use them a little later. Percent to mass, mass to mole, divide by smol, and multiply till whole if needed. So percent to mass, mass to mole, we're beginning at the mass step. Let's get both of these into moles. So you have 88 grams of carbon dioxide. Now, if you take a look, you have a periodic table available to you. They don't tell you it in this case. I bet they would. I may have just left it off. Molar mass of carbon dioxide is 44 grams, roughly. And that's because 12 grams for carbon and 32 for oxygen. So what you've got is 88 divided by 44 to get you 2 moles. You indeed have 2 moles of CO2. Similar idea with the water. You got 27 grams of water. 27 divided by molar mass of water is 18. Now, you can't use a calculator for this, but you see that you got 18 divided by 18, which gives you 1. And you have 9 left over. 9 over 18, that's a half. So you have 1.5 moles of water. What you see, now from the 1.5 moles of water, you have 2 moles of hydrogen for every 1 mole of water. So you can double your amount of hydrogen. This will actually give you 3 moles of hydrogen. And then this 2 moles of CO2 gives you 2 moles of carbon and 4 moles of oxygen. So you actually have 2 moles of carbon. So it's a 2 to 3 mole ratio of carbon to hydrogen. Which does that match up? Not this one, not this one, not this one, not this one. Aha. 2 to 3 or 4 to 6 gives you the same thing. So D is actually the answer. So think through that one a little bit. And let's finish up with a discussion that's not really related to moles as much as it's related to electrons, protons, and neutrons. So remember, this is kind of background information, but we can write isotopes in this way by saying the bottom number is the atomic number, whereas the top number is called the mass number. Remember, the mass number, or the atomic number, is the number of protons. And it tells you which atom it is, and that's the number on the periodic table. So for carbon, recall that 6 is the atomic number of carbon. The 56 is the mass number, which is protons plus neutrons, and that's always going to be bigger. So we're asking how many protons, neutrons, electrons. Because this atom is an atom, which means it has no charge, electrons and protons should be the same. So we're looking for 26 protons, which gives us these 2 possibilities, and 26 electrons, so both these are possibilities. Now the neutrons are not going to be 56 because 56 is the total of protons plus neutrons. So this one's out. So your answer is actually A in this case. Now what happens, remember how the periodic table lists these numbers as the masses, but what you do is you average all the possible carbon isotopes out there. So for example, you have carbon 13, you got carbon 12, and you got carbon 14. These are the 3 isotopes of carbon out there. By the way, this number is also the mass number. So you can rewrite these as carbon 13, carbon 12, carbon 14. You can omit the atomic number since that is very well known since you've got the periodic table for that purpose. Now all 3 of these are averaged, the masses of all 3 of these are averaged to give you this atomic mass. This is actually called the average atomic mass. And it has to incorporate all 3 of these. into it. So what happens is if we just took a straight average, then the average should be about 13. But it turns out you have to consider the abundances. How much of the total in nature is of that kind? And it turns out that an overwhelming amount of carbon out there is carbon 12. That's why the mass matches carbon 12. So some elements, if the mass isn't, a famous example is chlorine, it's 3545. And there are two isotopes of chlorine. There's chlorine 35 and there's chlorine 37. So what you can conclude from looking at this number is that the more abundant isotope in nature is this isotope right here, since the average mass is closest to it on the periodic table. So let me show you a question that actually incorporates that idea, as we have just a few minutes. And that question would be at the very end. I actually put it as a, here it is, as a bonus question. So let's take a quick look at that. So we have the atomic mass of copper is 6355. That's what you see on the periodic table for copper. Given that there are only two naturally occurring isotopes, 63 and 65, the natural abundance of 65 must be approximately what? So we know that the 65 is less abundant because the mass is 63. Again, there is copper 63 and copper 65 out there. Since the mass matches more for copper 63, we know copper 65 should be less abundant. So it can't be more abundant. It can't be 70%. It can't be 90%. It can't be half, because if it were half, this would be exactly 64. So it's between 25 and 10. Now, this here looks to me like halfway between 64 and 63. So we're actually a quarter of the way from 65. This would be the answer. In other words, from 65 to 63, if you say there are four parts, you get 63.25. Then you go to 63.5. You get 63.5. Then you get to 64. Then you go to 64.5 and 65. So this number is 1/4 of the way here. If that makes sense. Hopefully that makes sense. All right, so this concludes the second video. I'll put up the third video about the free response questions of this review.